It's a science publication. We are publishing a couple of magazines. One is in Tamil, other one is in English. Tamil, this is Tulir. It started from 1987 onwards. And Jantar Mantar is in English for college level students in 1991. And apart from that, we also have a couple of other magazines. And we also publish a lot of books, science books as well. If you visit the Tamil Nadu Science Forum website, now you can see all the list of books and you can place order online. And the third activity which we are working on the education and health. And the fourth is we want to bring more women in science, and we have an exclusive setup for encouraging women to participate in STEM activities, and that's called the SAMAM. So we are working in 5 different verticals, and I want to make an appeal to you through this platform to become a member of Tamil Nadu Science Forum. It's only 30 rupees subscription per year, and you will get a magazine called Vinyana Chiragu every month. So become a member of Science Forum, and you can, depending upon the interest, you can be part of any of those things. You can do research on education, you can work on the SAMAM, you can work on the development, you can working on environment, you can work on science communication, you can working on science writing. There are a lot of exciting activities are there. You can be part of Tamil Nadu Science Forum. So I want you to make member of Tamil Nadu Science Forum. We will be displaying you the QR code to become the member. Once you scan the QR code, you will get a form, fill up the form and send 30 rupees through Google Pay. You become a member. That's simple procedure. So now let me invite Dr. TRG to introduce the speaker.
Thank you. So this is the 89th Popular Science Lectures. So happens I was the first one to give the talk from 7 years back. Okay, 7 years back, and I'm very happy. In fact, my friend Siva is giving this talk. Actually, he's given earlier once, and since he wrote this article in Hindu, about quantum computers. There was interest from many of the organizers that we should have a meeting with him. And our organizers like Vijayan pestered him for a couple of months, and he did agree. And finally, we have to wait for the courses to be over in the university, Kriya University. Both of us are associated with that. And fortunately, it is over, or it is getting over. And so he has agreed to come today. And the quantum computers, Shiva was actually earlier working in IGCAR, in Indira Gandhi Centre for Atomic Research. And he has a lot of experience in various aspects of theoretical physics, in addition to directly be in touch with people who are doing experiments. So that way he is very good. And he was also associated with me with the Chennai Mathematical Institute for a short period. Then he moved to Kriya University. Then I also moved with him to some extent for the past few years. And he has set up the whole program there. And it is a great opportunity for all of us to understand, learn from him about quantum computers. And I look forward to participation by students. Usually our physics talks are well attended. And of course, a topic like quantum computers, which is very modern, has all more attraction. And now I find some of the students are there who don't have a seat. Hopefully something will be arranged for them. I'm sorry, it should be done soon. Now I request Shiva to start his lecture without much ado. Keep it so that is for the
room. Only for YouTube. Other one is for here.
And I can put it in the pocket.
Good morning. At the outset, let me thank Tamil Nadu Science Forum. Am I audible? Okay, I'll hold it closer. Okay, good morning. At the very outset, let me thank Tamil Nadu Science Forum for the opportunity. It's always a pleasure to be talking to people who are not from your research area, because very often those meetings get very acrimonious in a good sense, okay? Because we fight over concepts, we fight over principles and so on and so forth. But this is something where, okay. Maybe I'll wait for a few. Am I audible now? This is. I have it with me. Oh, okay. But I'm not very comfortable doing this way. Oh, okay. It's okay. It's okay. No, I'll manage. So I was just telling that I would like to thank Tamil Nadu Science Forum for the opportunity. And it's always a great pleasure to be here and talking to people. And this particular topic, as Professor TRG pointed out, the request to talk on this came after I wrote an article in Hindu. The reason for writing that article was Google had just announced the new quantum computer chip, Willow, and that was a kind of revolution at that time. Okay, and it's still not at a stage where you can expect quantum computers to be available in a store in Srinagar or somewhere. We are far away from that, and probably there is even a question of whether do we all need quantum computers? Okay, because looking at the kind of power that can exhibit, probably we will never require quantum computers at home. So because it's so very powerful when it is made. We are far away from that situation. So let me start with that. I don't know whether it's a warning or a good sign. We are far away from actually realizing a quantum computer, but we are almost hopeful. I would say in a matter of about 10 to 15 years, probably reasonably large quantum computer would be available on which you can do meaningful calculations. Okay. In order to, because this is a public lecture, I thought I would start with some very elementary or rather rudimentary ideas about classical computing, then move on to quantum computing. There is no smooth transition from classical physics to quantum mechanics or quantum ideas. There is always a jump, okay? And this jump will be there in this lecture as well. Some things I will ask you to sort of take on faith, and there is no other way because it is all that I have an hour or so to explain. But there are fantastic books and lectures available now. Okay, so post this lecture, if you are intrigued to go and listen to those lectures or start reading a book, I think the purpose is solved. Okay, so with this intro, let me start. So quantum computers, what are they and what do they matter? So these will be the major topics for our discussion. What are they? So I'm not going to discuss in detail how they are constructed and so on and so forth. Those are technological details, and even I'm not familiar with those things. Okay, I don't work on those aspects of quantum computation. And why do they matter? And so I'm going to give you a few instances where it could do both great wonders and it could also threaten you. Okay, and we should always be aware of both sides of any technology that you develop. Okay, and I do not know how many of you know about the place where I work. It's called Kriya University. Geographically, it is located in Andhra Pradesh, so it is just 70 kilometers from Chennai. Okay, so the mission is to help humanity prepare for an unpredictable world. That's the mission set by the first academic committee, and we have been sticking to that mission to the extent that I know fairly well, and we are actually trying to help students to develop or sort of grow as leaders who can actually help humanity in a responsible and ethical way. And this is the top view. Of course, we have a few more buildings now. This is a slightly older slide. I can also tell you that our university receives almost 40% of its electricity from solar power. Okay, so we have a huge solar harvesting unit there, here, and that gives almost 40% of our energy requirements. And this is the main academic building, and this is where most of the classes happen, but we have a similar building by the side as well, and research labs and a reasonably good library, I would say. Okay, so we have two schools, School of Interwoven Arts and Sciences, that's where TRG and I work, and we have also a graduate school of business, and we have a bunch of research centers associated with this university. Okay, they are all standalone centers. They generate their own fund. They have been consultants for many state governments in India and also to central government on policy implementation, efficacy of the policies, and so on and so forth. And they do lot of data analysis. Much before data science became the buzzword, these people have been involved in generating actual data, analyzing, and sort of informing policymakers what would work and what might not work. Okay, so the points for today's discussion would be a very brief introduction to classical computing, quantum ideas, then slight introduction to qubits, some typical quantum algorithms that one should be aware of, quantum computers, and what are the institutions involved in research activities worldwide. Okay, so I would like to remind you that year 2025 is the International Year of Quantum Science and Technology announced by UNESCO. And the mission statement of this declaration is, helping others to learn more about quantum on the centennial occasion, or simply taking the time to learn more about it themselves. So this will be the motto that will drive this lecture, helping others to learn. And if you start learning on your own, then I'm very much contributing to this occasion of International Year of Quantum Science and Technology. Okay, let us start with a very elementary introduction to classical computing, very basic ideas. So I'm starting with 1951, when we had a computer called UNIVAC. That time it was much talked about computer. And what this computer can do, this is the biodata of this computer. Born in 1951, weighed 7.6 tons, 125 kilowatts of power, that is 125 iron boxes being used simultaneously, and its clock speed is 2.25 megahertz, and it can do roughly 2000 operations per second. Okay, nowadays people talk about gigahertz, megahertz, and gigahertz, and this computer weighing 7.6 tons could do about 2000 calculations per second. That is, it can add 2000 single-digit numbers in 1 second. That's all that it could do. And it occupied a hall, it may be half of this size. Okay, that's the computer that was there. Okay, now what is it that we have now? Okay, we have something called a monstrous computer, which is with the Oak Ridge National Laboratory, ORNL. Of course, this weighs 270 tons, but it consumes 21 megawatts of power, something that is enough to drive a naval ship. Okay, and what it can do 10 power 18 floating point operations per second. Okay, so somewhere from 2 into 10 power 3 to 10 power 18, that is the scale. Now you may wonder, maybe you will have gadgets which will be few orders of magnitude more than what UNIVAC could do. Not so. Here is it. So Apollo 11 guidance computer, which was on Apollo mission, which landed on moon, it could work at about 12,000 operations per second. Okay. Then Cray 2, many of you might have heard about this phrase, Cray computer, that could do about 1.9 billion flops. If you have an Apple iPhone, that can do 11 trillion operations per second. Okay. So Apple, that iPhone that you hold in your hand, is 5,000 times more powerful than the supercomputers of 1980s. Okay. So this is the kind of technological evolution that's happening. Revolution, I should say, not evolution, but revolution. Now it sort of raises the question, when the technology is going at this pace, do we need an alternate technology at all? Maybe in a few years down the line, 11 trillion can become 100 trillion operations per second, and you can crack everything that you need to crack. Is that true? The answer is no. All these computations are inherently deficient. Okay, let us see what is that. So with the best supercomputer that we have now, all that we can do is a simulation of just 40,000 electrons in a quasi-crystal, okay, made of about 2,000 ytterbium and cadmium atoms. And that is a system which you can't even see. So these supercomputers will be able to predict property of such a small system. Anything beyond that, supercomputers will continue to work forever. They will not be able to produce a result. And okay, this you may say, hey, I'm not interested in this kind of exotic material. What is of more concern for me is, will it rain today? Will it rain tomorrow? And so on and so forth. Once again, with the supercomputers, your resolution is just 3 kilometers. So within 3 kilometers, I won't be able to tell you where exactly it will drain, where exactly it won't drain. Okay. And all this done with supercomputers. So obviously it tells you the way we process information probably is not the right way to process information. We need some paradigm shift in the way we process information. Okay. Though these are all, right from UNIVAC to the best supercomputer that you have, all of them work on almost similar principles. Not that supercomputers, of course, there are excellent, very creative designs there, but at a very fundamental level, they all work on the same principle, basically how to count numbers. Okay. So if you teach children how to count, of course, you will say, no, don't show any finger. That means nothing. 1, 2, 3, 4, and so on and so forth. And when I have exhausted all the 10 fingers, I will say, I have exhausted 1 unit of counting. Now I am going to start. If I have not started, it is 10. If I start, it becomes 11. So 1 unit of both the hands. And then the next time I start 11, then 12. Once I finish 2, it becomes 2, 0, 2, 1, 2, 2. So that is the way we count, and it's quite a natural thing to do. On the other hand, let me say I tie your hand back and you are allowed to count only with 5 fingers. What would you do? Of course, when there is nothing to show, you will say 0. Hold all the fingers. 1, 2, 3, 4, 5. Okay. And when you say 5, I have completed all the fingers that I have. Therefore, that 1 unit is done. I have not started the next one. Therefore, it is 0. So 5 that you represent with the 10 fingers is represented as 1, 0 if you are allowed to use only 5 fingers. Okay. Then, of course, 1, 1, 1, 2, 1, 3, 1, 4. Then 1, 5 means I would have used it twice. Therefore, 2, 0. Then the next finger, 2, 1. 2 times I have used the set of 5 fingers and then 1. So this is what they call base 5. Now it must be quite obvious. You can work with any base. The simplest one that one can think of is base 2. Okay. That is just to use 2 numbers. Let us say right hand and left hand. When I don't raise both the hands, it is 0. When I raise right, it is 1. Okay. And then raise 2, I have used both the hands. That is 1 unit. Therefore, 0, 1, I have used both. Then the next time I have used both the hands once, and therefore I think I have started using 1, 0, 1, 1. Then I have used both of them, it moves to the other one. Therefore 1, 0, 0, because I cannot use 2. 2 is not available for me. It is only 0 and 1. And that's how I set it up. So this is called a binary system. Okay. Now the advantage of this binary system is it has got just 2 symbols. So if I have a way of representing these 2 symbols using some gadget, then I have actually a way of representing any number. Instead of having 10 symbols, I can just work with 2 symbols. Okay. Of course, 2 symbols are not enough for an alphabet. You need more of them. Let us see how we actually manage that. Okay. Here is an example. The number 8 that we are all familiar with in the so-called decimal system is 10 power 0 times 8. Any number power 0 is 1. You will take it as a definition for the time being. But you can also write it as 5 into 1. 5 into 1 plus 5 power 0, 1 into 3. Okay. So 5 plus 3, that makes it 8. Therefore, 8 is represented as 13 in the base 5. That is, you have only 1 hand to use. You can also represent it using 2 fingers, like 2 power 3 into 1. You don't have to use 2 units anytime, 1 unit anytime, 2 power 0 anytime. Therefore, it is 1, 0, 0, 0. So now you know how to go back. Given a decimal number, you can go to binary. Given a binary number, you can go to decimal. So because your language is in decimal, you don't speak in terms of ones and zeros. You speak in terms of 0 to 9 and their combination. But we know how to actually go from this to this. Okay. And computers, all of them use binary system. Your cell phones, your supercomputers, doesn't matter. They all work with this binary system. Okay. So let me just to tell you what these computers internally do. I'm going to give you an alphabet chart, something like you show in your LKG class, right? A, B, C, D. These are all the alphabets that make up the language. And here is an alphabet. I'm going to use just 3 symbols. So I'm going to represent A as 1, 1, 1, B as 1, 1, 0. 0 is 3 zeros. 1 is 2, 0 followed by 1. And then these are the symbols. So I have a representation for 2, for space, for comma, and full stop. Okay. The rule that I have is read given any sequence of such numbers, read them in packets of 3. Okay. Because I'm using 3 digits to represent any particular letter. So read them in packets of 3. So here is a binary sequence. Read in packets of 3. and what this binary sequence represents. That's the question. Quite easy. 110. I have to just go back and look. 110 is B. The next three is 111. That is A. So there we go. So this actually reads as Baba space 12 dot. Tells you that if I have numbers, I can even represent your language. Okay. So I can make computers understand what is it that you have written. Okay. Well, how do you process this information is a different question, but at least everything that you can communicate using the vehicle that you use for communication can all be represented just using two symbols, 0 and 1. That's it. Of course, if you have more number of symbols to represent, you will not be able to do with the 3. You will go to 4, 5, and so on and so forth. There's a very famous tabulation called ASCII. And that gives you, that's what all computers follow. And that tells you all the symbols that you have on the keyboard could be represented with that, including capital letters and so on and so forth. Okay. So what is the advantage of binary? It is simple and general enough. That's the first criterion. It is simple and it is general enough. There is nothing that you cannot represent using binary. The more important one is technological implementation is fairly easy. Instead of having a gadget which can actually tell you I am in state 1, state 2, state 3, state 4, state 5, you can only say I am in state 0 or 1. I am turning to the right or I am turning to the left. Much easier to figure out. On the other hand, I say I can turn in any of the 20 directions. I'm here and here, there will be a confusion whether I'm pointing close to east or slightly away from east. Okay. But when you have just 2, it is much easier to discern in which state the system is. If I'm going too fast, please let me know. I will slow down. Okay. So this is a very famous statement by a physicist, Landauer. He said, information is physical. Okay. What did he actually mean when he said information is physical? You can say 0, 1, all these things, but you need somebody to hold this value 0. You need somebody to hold this value 1. Therefore, you need physical gadgets to hold these values 0 and 1. And any physical gadget will have to obey the laws of physics. Therefore, bits have to follow the rules and regulations put forth by the laws of physics. Okay, that's the importance of his work. It appeared in 1970 or so, but then he wrote a very beautiful article summarizing his ideas in Physics Today in 1991. Okay, so a physical gadget is required, of course, to host the bit. For instance, it could be on-off condition of a bulb. When this is on, I'm going to declare it is 1. When I switch it off, I'm going to declare it as 0. So in principle, you can make a computer with bulbs, but you should be really, really fast to switch on and off all these compute bulbs, and you can represent how numbers are there and how they change when you perform calculations. Okay? It could be rising left hand, right hand. That could be 0 and 1. Okay, but the current technology doesn't, of course, use any of this. It uses something known as the transistors, and from transistors, we have sort of evolved to something known as CMOS, complementary metal oxide semiconductor transistors. Let us not worry about what they are. They are extremely tiny, and they can stay in the state of 0 current or some high current. Or if you understand voltage well, it will be very close to 0 voltage and very close to 5 voltage. When it is 0 voltage, I will see this gadget is representing 0. When it is close to 5 volts, I will say this gadget is representing 1. And this can switch on and switch off in a matter of picoseconds. Okay, that fast they can switch on and switch off. Okay, and if you now make a measurement on this, it will tell you in which state that gadget is. This measurement itself does not change the state of that. Okay, this is an important point that I would revisit when we go to quantum ideas. So we have binary digits. We can represent binary digits using semiconductor gadgets, small gadgets, and the numbers 0 and 1 are represented by the state of the gadget in terms of current, low current or high current. And the thing is, when I make a measurement, because I need to know what it represents, I need to measure. So when I make a measurement, that doesn't change. When the system is in high, that is 5 volts. When I make a measurement, after measurement, it remains in 5 volts. It doesn't change. Okay. Okay. So we have bits, we have physical gadgets hosting the value of these bits, and there are something called gates, just named enough. What these gates do, they change the value these bits hold. Okay, it is by combining gates that we perform information processing or computation. For instance, a simple one could be, if the gate is holding 0, flip it, make it 1. If the gate is holding 1, flip it to 0. This is one operation that you can do. There are many other operations that you can do. This is a simple operation that you can do. But if you have 2 bits, you can do something known as OR, which we all use. Okay? I will go to cinema or cricket match today. That OR means there is a choice that you have to make. Okay. Now, both can be true, both can be false, one can be true, one can be false. And what is the result? That is the logical OR gate, and that's what it is. If both are 0, output is 0. If one of them is 1, output is 1. Even both are 1, output is 1. This is another process. So I give an input 0, 1, but the output is 1. So this is the process. Turns out any mathematical computation that you need to do can all be converted into a sequence of these operations. And that's what the computers do. Of course, they do it so very fast, and they are able to crack problems which are humanly otherwise impossible. Okay. Of course, when I gave this talk first time long back, somebody read it from a distance. He said, Bill Gates. I said, no, it is Bits and Gates. Surprisingly, his name has that phrase Gates. And these are some very well-known gates, and they occur everywhere when you do digital electronics and so on. Okay, now one thing I want to stress is quantum theory is absolutely essential if you want to understand how the CMOS transistor works. Okay, but that does not make it a quantum computer, because at the end, the CMOS transistor still represents only zeros and ones as low voltage and high voltage. Okay, so you could have replaced the CMOS transistor, as I told you, with all students in your college or school. Raise your right hand and left hand. That would equally well do the job. It won't be fast, but it will do the job. Okay, so it is still a classical computer, though the semiconductor working itself requires quantum theory to understand. Okay, now there is something known as Moore's law, which sort of tracks, or Moore proposed it sometime in 1960s. He said almost every 2 years, the number of transistors on a chip is doubling. Okay, so we started with somewhere around 5,000 chip. Usually it's about slightly lower than 2 centimeters square. That's the area of a chip. And where are we now? It is about 5 followed by 10 power 10 transistors on a chip. Now you can imagine the size of a transistor. Okay, something like a 5,000 on a chip, that is 5 into 10 power 3 to 5 into 10 power 10. So you don't even need one Avogadro number of atoms to make a transistor. You need something like a 10 power 8 or 10 power 9 atoms to make a transistor. The technology has improved so drastically. Okay, and this is that curve that Moore suggested in 1980, but it seems to be fairly okay. Can it continue forever? The answer is no. As you make things smaller and smaller, quantum effects will start dominating. And what you typically think a transistor should do, hold 0 or 1 until I disturb it, that's not true. It will change even if you don't disturb it, because you can never isolate a transistor from the surroundings. So quantum mechanics will start playing its role. Okay, now this is what I was talking about. In 1960, we had about 10 power 17 atoms per transistor. And of course, at that time, speed was not measured. 1970, we had 10 power 12, and the clock speed, that is, it can switch about 10 power 6 times a second. And the energy per step, that is for one switch, 0 to 1 or 1 to 0, that requires 10 power 2 picojoules. Okay, picojoule for per operation is very small, but when you do, let us say, 10 power 15 operations, you see it is already at the level of joules. Okay, and now imagine everybody hosting a computer at home, and you can see the amount of power that will be sort of feeding into these computers. Come 2018, it is 10 power 8 atoms per transistor, and the clock speed is 10 power 9, and the power consumption has fallen by 3 orders of magnitude. Okay, though it is very small, but the number of computers that we use and the number of let us say transistors on a computer, that has gone up. Therefore, the total power consumption has not really dipped. Okay, and now let me give you nice examples of where this is useful and where it is not very helpful. I told you these classical computers, though they are very fast, they have limited capability. We saw already that it could only solve a system with about 40,000 electrons. So when you send your, let us say, OTP, or the bank asks your OTP and transmits it via internet and receives and they process and then give you money, somebody should not steal your password and OTP and misuse it. Okay, so we have to protect it. So we have to encrypt this information and send it across, and then we have to decrypt and get it back. Okay. So encryption, unless you do a really, really complicated process, smart guys will always decipher it and get the information. In fact, it happened in World War II. Alan Turing was a master of finding out what messages were being sent. Okay. So in 1970s, three individuals, Rivest, Shamir, and Edelman, they proposed a scheme which will actually help you to sort of send messages across in a safe manner. And what did they rely on? They relied on the fact that if I give you a large number, it is very difficult to find the prime factors of that number. Okay, let me just explain this because it's a public lecture. Suppose I give you a number 10, you can write it as 2 into 5, but 2 and 5 themselves cannot be written in terms of smaller numbers. 5 is 5. 5 into 1 is all that you can do. You cannot further split it. Same is the case with 2. If I take 68, you can write it as 2 into 2 into 17. You cannot further reduce it. Okay, this is the prime fact number decomposition. Turns out, if I give you a 250 or 300 digit number and ask you to find the prime factors of that, that is very difficult process. Okay, it's a very hard process. Okay, and here is the nice story. In 2010, so sieving is one of the most efficient process. There are very many ways to find out the prime numbers, but sieving is the most efficient one that we know as of now. And it says on a single core 2.2 gigahertz AMD survey computer, like say our laptop, our computation required more than 10 power 20 operations, which will correspond to 1500 years. So if you are using a computer to crack the code that a bank sends out, it will take about 1500 years. But banks keep changing this code every 2 months. So by the time you are working on code 1, they would have changed it in 2 months, but you will require about 1500 years to crack the code. Remember, it is not impossible to crack the code. It is difficult. It consumes a lot of time, and that is the safety mechanism that you use. Okay. So the current classical computers are still not at a stage where they can work fast enough to crack this code in reasonable time, in a matter of days. No, it's not possible. Okay. And this is in some sense a positive aspect. The deficiency of classical computing scheme is helping us because nobody can crack this. So it provides some kind of a safety. But then there are other things. For instance, we know that no shipping lines, they transport liquefied natural gas from across the world, and there are warehouses where they store, there are points where they extract, where they liquefy, ... And what they have figured out is there are 2 power 10 power 6 possible ways you can bring, let us say, gas across the world. That is every possible path. Okay. Now we need to optimize because ships consume fuel as they move around. There is a warehouse costing and so on and so forth. So how do I optimize? What's the best way to move these goods across? Now, currently what they do is they split it into small. Within India, they try to optimize. Within Sri Lanka, they try to optimize. Then they put these things together. They think that locally or unit-wise optimized process will be globally optimized. Not necessarily. There could be another path which could be much cheaper. But if you want to really figure out what that path is, we need to really scan through these many paths. And the total number of atoms in the universe is 2 power 270. And the number of paths that I need to sort of scan through to figure out which is actually the optimized path is this. So obviously classical computers have no way of tracking this for us, at least in the immediate vicinity. Okay. And of course, we have flight design problems in Boeing, for instance, which gives the aircraft. We are worried about safety of aircraft particularly, and there are about 100,000 variables they look at. Just imagine each variable can take about 5 values. Then the number of combinations is 5 power 100,000. The current day computer just cannot handle this. So these are all practical problems. I can write down the problem, but the computers cannot handle. Obviously, the way we do classical computing is inadequate and will not be able to handle it. So bit-based computers are not powerful enough. Maybe can we harness the quantum? That's the next question that we can, but that's the only thing I have. If I don't have anything classical, obviously, as an enterprising population, we should ask, can we do something with the quantum? Okay, quantum ideas. I told you it was going like this. Now it will take off, and that's the way it is. And it's international era of quantum science and technology. Take this as a trigger to go and learn about quantum mechanics. Okay. So of course, I'm sure all of you recognize this guy. He's Richard P. Feynman, one of the most flamboyant and most creative physicists from the 20th century. And this is a statement from his paper, Simulating Physics with Computers. it is impossible to represent the results of quantum mechanics with a classical universal device. Okay, whatever mechanism you use, so long as the method of computation is classical, that is, bits are either zeros or one, and you maneuver their states, you will never be able to represent the results of quantum mechanics. Okay, of course, he goes on to say, nature, of course, is not classical, and why are you so worried about simulating it classically? So that's his argument. And there was another guy, of course, in being a mathematician, he was far more rigorous and precise, and he also came up with exactly the same idea. Okay, so both happened surprisingly in the beginning of 1980s. Okay, of course, once again, it is Feynman. He wrote a book called The Character of Physical Law, which is accessible to anybody, not necessarily physicists. Anybody can read this. I will take just this one experiment, which has been designed to contain all the mystery of quantum mechanics, to put you up against the paradoxes and mysteries and the peculiarities of nature 100%. Okay. Any other situation in quantum mechanics, it turns out, can always be explained by saying, you remember the case of the experiment with the two holes? It is the same thing. Those of you who did +1, +2 physics, all of you would have studied something as Young's double slit experiment. That's what he's referring to. You understand Young's double slit experiment? Sorry. When you don't hear, you just raise your hand, I will understand. Okay. When you understand Young's double slit experiment, you pretty much understand quantum mechanics. Okay. So the interference that Young's double slit experiment sort of provided as a clue to infer that wave, electromagnetic or light is wave, that phenomenon of interference is quite common. It happens even with water waves. Okay. This is some experiment that one can do in any university. We do it in our university. So you have waves generated by two tongues which are vibrating. So for the waves spread out, ripples essentially. And when you have just one tongue vibrating, you have these nice ripples. But when you have two tongues vibrating, that is 2 points from which ripples are spreading out, you will start seeing these nice patterns. This pattern is what we refer as the interference pattern between these two waves. So this is typically a characteristic feature of waves. They interfere, they produce waves. Of course, they have to produce the right condition, then they will produce the right pattern, but they always interfere. And this old experiment of Young has been voted as the most influential experiment in physics. Okay, you can do this experiment with waves like water waves. If you believe lights are waves, you can do this, but you can also do it with particles. Okay, and what does this wave do? When waves come in, that is, the peak of this wave aligns with the peak of this wave, the valley of this wave aligns with the valley of this wave. When you have two such waves, they will add, producing a bigger wave. And that's what I'm just saying. Wave plus wave in small letters is a wave in big letters. It produces a wave. But you can also arrange things in such a way that the peak of the first wave goes with the valley of the second wave, in which case they cancel. Therefore, wave plus wave can also be a no wave. Okay, but something that is not possible with particles. When you have particle plus particle, there are two particles. But when you have wave plus wave, it can be a big wave or no wave. Okay, this is something very peculiar about waves. So classically, we think, hey, there are two kinds of entities. We have particles which behave one way and waves which behave in another way. But then people right from 1930s knew that this is not true. There is actually no clear distinction between particles and waves. Whatever you classically call particles, those properties are possessed also by what you classically sort of called waves, and vice versa. Okay, and this will work now. I have a 2 minutes movie. What should I do? I press again. Okay. So here is a movie where the experiment was done with the electrons and not light. The electrons were sent one by one. And every time an electron was sent, they saw a dot on the screen, essentially like what you will get as a particle. Okay. Now it's a mango season. Of course, you take a mango stone and throw, it hits a mango and the mango falls. Therefore, it hits at a point. Those that the mango falls. And so that is a particle character. So what do you expect on the screen? Yeah, random distribution of dots because the electrons are going through two small holes. Let us see what the experiment actually revealed. Of course, the voice is not coming on. I'll read it for you. Now we are looking at the detector plane on the monitor. Bright spots appear here and there. These spots indicate individual electrons. Electrons are sent out only occasionally. Therefore, the chance of finding one electron in the microscope is very small, not to mention the chance of finding two. That is, two electrons to be there is very, very small. Since the electrons are detected one by one as particles, we have to conclude each electron must have passed through at random on either side of the biprism, which is the two slits, thus creating uniform distribution when without interference when accumulated. Okay, looks like a very random distribution of electron reception. Under such condition, do electrons form a uniform distribution? But look, we begin to see some fringes in the perpendicular direction that looks like interference pattern. Okay, since this experiment lasted for more than 30 minutes, I have sped the movie up. Interference fringes are now clearly visible. So if they really behaved as particles, it should be a random collection of points on the screen. If they really behaved as wave, right from the first electron, it should have produced interference pattern. It produced dots by dots, but you collect all the dots, you have waves. So when we describe interference experiment, remember I talked about constructive and destructive interference. So we say those two amplitudes interfere. Constructively and destructively doesn't matter, but they interfere. And that's precisely the idea here. That is, when you have to describe a system quantum mechanically, I only speak in terms of something known as a probability amplitude. What is the probability amplitude? Certain process will happen. Okay. And if I have two possible processes, A and B, the probability that both the processes will happen is also a possibility. Okay. Something like asking, let us say this room is locked and I put you here, you are a quantum particle. Suppose I ask the question, where are you in the room? And I make a measurement, you will be here. Under identical conditions, I come again and open the box and see it is possible that you are there. I started the system identically, but there is no way I will be able to infer exactly where you will be every time. Okay, there is only a probability that I can prescribe where you will be and where you will not be. So when we want to describe quantum systems, we move away from the classical way of saying this is exactly the state, 0 or 1. That is not possible anymore. 0 and 1 are possible states, but a combination of 0 and 1 is also a possibility. It's not a faulty transistor which produces somewhere around 3 volts. No, it's a transistor which exists in a state which is a combination of 0 and 1. Okay. Okay. That brings us to the next topic, which we call qubit. So qubit is the equivalent of classical bit. For us, classical bit means something which can take value 0 or 1. And what does qubit take? A qubit is a system with 2 states. I'm going to use this symbol just to say it is not my classical bit 0. Okay, it is the state of a quantum system. It could be, let us say, particle on the right is 0, particle on the left of this room is 1. That is a possibility. Okay, but this is a huge system. We can't make a computer with such a big system, but we need to really look at microscopic systems where these quantum effects are manifest, and you can sort of retain these quantum effects for some time. And what are those systems that you can take them to be 2-level systems? That is 2-state systems, spin half particles. You can have spin up and spin down like this. Of course, I put this figure basically because this statement is very amusing. Electron spin explained. Imagine a ball that is rotating, except it is not a ball and it is not rotating. So, but that's how they try to explain. It essentially tells you it is really difficult to explain quantum features. Okay, you have to sort of accept it and work.
Differently when we are not observing it or when the camera is not on.
You can describe completely, including the camera as part of the system. So theories know how to do it. Yeah. Okay. So, but typically the way to imagine and to begin with. Okay. This is one possible 2-level system. So you can use it as a quantum bit. Okay. Energy levels in an atom, for instance, calcium atom, there are many levels, but you can choose your lasers interacting with the atom in such a way, only these 2 levels participate in the relevant dynamics, and therefore it can again act as a qubit. In fact, the ion computer is essentially based not on an atom with 2 levels, it has many number of levels, but there are only 2 levels that participate in the interaction. You can talk of photon polarization. Okay, polarization is light is electromagnetic field. This has a direction of the electric field, okay? So it can be directed along in one direction, or it can be directed along the perpendicular direction. I call this X and Y polarized, okay? Which is X, which is Y is up to you, but that's what it is. So that can represent 0 and 1. X polarized light is 0, Y polarized light is 1, okay? You can have a Josephson junction. It needs explanation, but I'm not going to do. But this is the most promising technology to realize quantum computers. It's involved. It works at sub-Kelvin temperatures, but this is the most promising technology as of now we have, okay? What it does is, it again has energy levels like atom, but it is not an atom, okay? It is actually a chunk of material called a Josephson junction, put in a circuit, which circuit means it's actually, I should say, kind of a metal strip and things and forth. They act as capacitor and inductor. Don't worry if you do not know capacitor and inductor, doesn't matter. But it has energy levels. So these two energy levels will act as 0 state and 1 state. Okay. Okay. Now a qubit is a system with the 2 states, and these are all the possible 2 qubit system that we discussed. And I told you in the case of quantum mechanics, 0 and 1, yes, they are possible state, but it can also combine and produce a new state. Okay. And I represent it is by alpha 0 plus beta 1. Okay. In fact, multiplying a bit, classical bit 0 doesn't make sense at all. I cannot have a transistor in state 0 and half 0. No. I cannot have a transistor in state 1 and 0.81. Such states don't exist. Either it is 0 or 1. But in quantum mechanics, I can have alpha times 0 plus beta times. Remember, this is the 0 equivalent of classical bit, 1 equivalent of classical bit. Okay. What are these numbers, alpha and beta? They are called complex. They are complex, not called. They could be complex numbers, but don't worry about what they are. You can actually, from that number, you can find out what is the probability that the qubit will end up in 0 when you try to see in which state it is. This is the deviation from classical computing. I told you, when the CMOS transistor is in state 1, if I look at it or make a measurement to see in which state it is, I find it at 1, and after measurement, it continues to be in 1. So again, you can go and measure, it will be 1. Again, you can go and measure, it will be 1. But when I try to measure this to find out whether it is in 0 or 1, it will give you a value, but after that measurement, it will not be in this state. It will be in whatever value you measured, 0 or 1. Okay. So in fact, by knowing that it is in 0 after measurement, you have no way of telling what was the state before, because this only gives me a probability that will get into 0. Under identical condition, it can also give you 1. Okay. This is the subtle aspect of quantum mechanics. Looks like you got. It is not even certain about what the state is. How is it going to help us do computation? But precisely, this is what helps us to do computation faster and in a more powerful way. Okay. So this is a statement probably worth remembering. Classical, that is physical bits, classical QE bits can exist only in one of the 2 possible states, 0 or 1. Okay. Now, I told you qubit state. This is just a representation of that. It's not really required. I'm going to skip this. And these are all the things that I summarized in the previous slide. Okay. Now, let us look at what these states are. These are just a symbol. I have 2 qubits. You can have very many classical bits to perform computation, right? That's what you need on a computer. I can have 2 qubits. So first qubit is in 0 state. Second qubit is in 0 state. It's perfectly clear. 2 qubits, both are in state 0. The corresponding classical equivalent will be 0, 0. That is transistor in 0 state, transistor in 0 state. I can have this, both the qubits in 1. The corresponding classical is 1, 1. Fine. But quantum mechanics tells me, remember that Young's double slit experiment, they can also be in a combination of both particle and wave kind of. It can be in a state like this, 0 plus 1, a superposition for the first particle, first qubit, but the second particle is in the state 0. Okay. First qubit is in a superposition, second in state 0, there is no classical analog. You do not have a classical bit as a combination of 0 and 1. It is either 0 or 1. Okay. Even more interesting, probably this actually holds information about quantum mechanics, is a state like this. This I understand. 0, 0, first qubit 0, second qubit 0. First qubit 1, second qubit 1. But quantum mechanics tells you if there are 2 possible states, a combination is also a possible state. Therefore, this should be a possible state. Now I ask the question, what is the state of the first qubit? If you focus on this and say it is 0, no, somebody may say it's 1. Okay. Same the case with second qubit. The whole system is in a definite state, but individual systems are not in any state. Okay. This holds all information about the fundamental aspects of quantum mechanics recognized by Schrodinger way back in 1950. Okay. And of course, it is not possible to have such a situation in classical physics. Okay. Schrodinger, I'm sure all of you would have, at least in movies, you would have heard about Schrodinger cat, ... It's a highly technical thing. He actually wrote a paper, The Current Status of Quantum Mechanics. And there he talks about why quantum mechanics is very weird. Okay. I don't know whether I should use the phrase weird. And of course, later on, people said it's very cruel to say the cat dies. Therefore, instead of saying it is dead and alive, I'm going to say it is awake and asleep. Okay. So the situation is something like this. There is a vial here which contains radioactive material, and the radioactive material emits. It is going to break open a poison, a bottle containing poison, and that poison in turn will, okay, not poison, maybe a chloroform or something that will put the cat to sleep. Okay. If the radioactive material doesn't decay, the chloroform doesn't come out, and therefore the cat continues to be in awake state. Okay. Now the whole thing is done and it is shut. So before I started the experiment, the cat was awake. The radioactive material had not decayed. So I know what the state is. I close it. The radioactive material has a half-life about 1 hour, let us say. I ask, if I open this in about half an hour, what would be the state? 1 hour half-life means it can also decay half an hour before. Okay, that's only an average of lifetime. So it could be an active nucleus and an awake cat because it has not reduced chloroform, or it could be a decayed nucleus and a cat which is sleeping. Both are possible. If these are possible states, of course, quantum mechanics will tell you that this plus this is also a possible state. It is very easy to understand this. Hey, it has not decayed and therefore the cat is awake. Oh, it has decayed, therefore the cat is asleep. But when you have not opened and you have not figured out what has exactly happened, until then you have to assume that this is the state. That's the best information you have. Okay. And this is what we said 0, 0 plus 1, 1, if you like. Okay. And he said it is not the one, but rather the characteristic trait of quantum mechanics. Entanglement, as it is called, that is actually the characteristic trait of quantum mechanics. Okay. Why is it useful? Looks like very philosophical and mind-boggling, perplexing, whatever phrase you want to use. Is it useful at all? The answer is yes. Okay. Now, I have some more time. I need at least half an hour. Thanks. Okay. Okay. Is entanglement a resource? That's the question we ask. Okay. So let us start with a very simple game. Suppose there are two persons, you and your friend. You possess a coin each, and each coin has a head on one side and tail on the other side. Okay. Now you are in different places. You have your coin, your friend has her coin, and you have made an agreement. I will send you my coin in head, and if you also head, then you will get, B will go to A's house. Okay. Then A will send coin in H, and B's coin, she has kept it in tail. B will not go to A's house. And there are 4 possible choices. Okay. Suppose we want to explore all the 4 possible choices. Is it possible to communicate by sending one coin? Let us assume the A wants to send with the H. Then A can manage this option and this option. These 2 options are not available for her because she has chosen to send her coin with A. H does the output. B can be having anything, H or T, A doesn't know, but these are the only 2 options that can happen. If A chooses to use tail, of course, these are the only 2 options that she can have. Now, question is, can I manage to communicate all the 4 possibilities and decide, depending on my choice, which of any of the 4 I will be able to tell B, let us do this. Okay. Turns out it's possible using quantum mechanics. Let me quickly, slightly mathematical, but not difficult. Okay. Let me explain, take you through that. Okay. So as I told you, we can put systems in superposition. Okay. Imagine this as 0, 0 plus 1, 1, like your qubit. In fact, the coins could be 1 qubit with A, 1 qubit with B, but initially they have prepared the whole system in 0, 0 plus 1, 1. Is that clear? I know it's difficult to comprehend this, But imagine, always go back to that example of 0, 0 plus 1, 1, replace h with 0 and t with 1, you are through. Okay. Now I'm going to do certain manipulation. That is, A is going to, A doesn't have access to B's qubit. A has only A's qubit. But the whole thing is put in a system like this. But A can manipulate, like A could, send H or tail. A can manipulate her qubit. And let us say A has one operation called X. If she has a T, it will change it to H. That is, she will simply flip 0 to 1. Okay. She can do Z. That is, if it has a tail, it will become minus tail. You remember, we could put a number alpha in front of the stage. It will be minus 1 times tail. If it is head, she will not do anything. And she can combine the two and produce this. That is, she can change H to minus T and T to H. These are the three operations she will do. What does she have? She has her qubit. Both the qubits together are in this state. Now let us see. Okay, now let us see. This operation X on the state, what does it do? It changes T to H and H to T. Therefore, H will become T, T will become H. The second parts won't change because they are with B. A cannot change that. Okay. Now let us look at this. Change T to minus T. So AB is H, H. Therefore, this doesn't change because first letter is H, but the second letter is T. That operation says she will change it with a negative sign. Therefore, it is minus TT. And of course, do both, you will get the state. Okay. These are the three ways A can change the state of the whole system just by maneuvering her qubit. Okay. Now what they do is, okay, if you send me TT plus HH, that is the state that they originally started with, B will go to A's house. If the final result is HT plus TH, B will not come to A's house. And the fourth choice. These are four different states. And A has to manipulate only her qubit. He doesn't have to touch B's qubit. Okay. Now, if she wants to execute option C, she will put Z on her qubit and ask B, now you find out what the state is. Of course, B will find the state to be this, and therefore B knows what is to be done. Okay. Now, all the four choices A can execute, which is otherwise not possible with the classical coins. Okay. And in technical parlance, they will call it dense coding. That is, with just one qubit, you are able to send 4 bits of information. Otherwise, you'll be able to send only 1 bit of information. That's it. Okay. Now, C bits and Q bits, just to rephrase, 2 classical bits can represent any one of them. Both can be 0 state, first 0, second one, vice versa, both can be 1. But in quantum mechanics, of course, you can have the corresponding states, but quantum mechanics also allows for superposition. Therefore, I can represent all the states in one go. I don't have to produce. Suppose I represent all the 4, I need 2 qubits for this, 2 qubits for this, 2 qubits for this, 2 qubits for this. Simultaneously, if you want to represent. One by one, you can represent using just Q2. But if you want to represent them simultaneously, I need all the 4 pairs of qubits. But here, just with 1 pair of qubit, I can represent all of them in one go. Okay, now what happens here? Here I have 8 possible combinations. I need either 8 packets of 3 qubits, or I have to repeat the process 8 times to represent them. But in quantum mechanics, one go. 3 qubit, you have all the 8 states represented. Okay. Okay. Now, this possibility of representing or encoding information simultaneously allows you to perform shapely.
That I could understand.
Yeah.
Two spins, both spin up, you become different state. But top and 1, or 1 up, another down.
Yeah.
2 down. Those 4 states up to that I could understand. How? What is it? Entanglement. That is what.
Yeah, I'm not sure whether we can have a physical mechanism of explaining it. In fact, one of the main lessons in quantum mechanics, I would think, my important lesson students would get is, you can never make a mechanical model which will mimic quantum mechanics. Just cannot make. So that way, physical model is simply an impossibility.
The state that we have initially are common to spectrum.
Absolutely. Yes.
But in what way, one state being in 0 will be able to make the other state in 0 or 1?
Which state you are looking at? Let me just go back.
That is where the entanglement
Yeah.
brings some kind of, I don't understand what to do.
We'll continue with that. So yeah, that understanding is a slightly loaded word. It's difficult for me because we need to question we need to ask what it means to understand. But I told you how it is useful. We will talk about entanglement a bit more later. Now, what are quantum algorithms? Algorithm is essentially a sequence of steps to execute a problem. Suppose, let us say you came to the library in the morning. You could have actually written an algorithm. Take out the scooter, go on Raj Bhavan Road, Vallabhbhai Patel Road, come near that circle or that signal, take a right turn, then take a left turn, park your bike or scooter, take the left, come to the 4th floor and attend this lecture till the end. Okay, that could be the algorithm. So it's essentially a sequence of steps that are connected to each other, and that defines an algorithm. So we can also have a quantum algorithm. I'm not going to describe what these algorithms are. They are ingenious creations, I should say. Sorry. Okay. The first one I'm going to say is something known as a Deutsch-Joshua algorithm. To the extent that I know, there are no practical utilization for this algorithm, but it actually, at the time when they wrote down the algorithm, it brought out the power of quantum computation. Okay. Let me say I have 4 functions, F1, F2, F3, F4. These are 2 digits. Forget about the first digit. Okay. It could be 0, 0, 0, 1, 1, 0, 1, 1. If it takes the same value for all the inputs, we call it a constant function. Okay. For every possible input, it could be 0, or for every possible input, it could be 1. So one which takes 0, I call F1. One which takes all 1, I call F2. The other possibility is for 2 of the inputs, it can take 0. For other 2, it will take 1. So these are the possibilities. Okay, you can list down all I have just listed down 4. Okay. Now the question that I need to ask is the function constant or balanced? I am already told it is member of one of these two. It's not an arbitrary function. Either it is a constant function or balanced function. Okay. I need to figure out. Suppose I give it to a classical computer. What it will do? It will calculate the value for the first input. It will calculate the value for the second input. Let us say both of them turn out to be 0, 0. It has to still calculate the third input to know whether it is constant or balanced, because 0, 0 for the first 2 doesn't mean it is constant, because the third one could be 0 for constant, it could be 1 for balance. So you need to perform 3 computations to decide whether this function is constant or balanced. When you go to quantum mechanics, I can represent all these inputs in one go as a superposition. You just need one measurement to decide whether what exactly is measured is the smartness of Deutsch and Josh. But I'm telling you, with just one measurement you can do. Why is that possible? Because I can represent all the inputs in just one superposition. Okay, that gives you the power. And independent of the number, in fact, if you have, let us say 256 inputs and it is constant or balanced, you have to do at least half of 256 plus 1, which is how much? 129. Calculations you have to do minimum on a classical computer, but on a quantum computer, just independent of the size of the input, it will always perform this decision with just one calculation. Okay, those of you who are interested in how exactly the algorithm does, fantastic books are there. Nielsen and Chuang is a nice book which will help you. Even Wikipedia has a decent article on this. Okay, this is one. Now it utterly tells you how superposition enables quantum computer to be extraordinarily fast. Okay, in the initial days they called it infinite parallelism, because if I have a large number of inputs and if I have large number of computers, simultaneously I can calculate the output for all these inputs and then do one comparison and get it. Okay, but then I need very many number of computers running in parallel, whereas a single quantum computer that way is going to mimic a host of classical computers running parallelly. At stretch of imagination, they said it is infinite parallelism. Okay. The next one, of course, is the familiar one. By now you are familiar with this, how the classical computers are good for us because they cannot crack this code. Lucky that quantum computers are still not around. I'll show you the graph. I'm not going to tell you how the thing is. It's a fairly involved. So if I have a n bit, it could be 1,000 bit. Typically they use about 1000 plus bits to send information. If I have 1000 bit, and if I have a quantum computer which operates at 1 gigahertz, it will crack the code in about 120 seconds. And your banks usually give you about 3 minutes to key in your code. Okay, this will crack it in 120 seconds, whereas a classical computer operating at 10 PZs will require about 1000 years to crack this. Okay, so if you actually make a quantum computer which can work reliably, RSA is out. Okay, we need, of course, there are other quantum encoding algorithms available, but they have to be tested. Nobody is sure, because proving that these are safe is again a very deep mathematical problem. So, and Grover search algorithm, by the way, Indians have plenty of contributions in the field. Okay, so many names you will see, algorithms named after fantastic scientists from India. Okay, so identifying a pattern in a long list of unsorted patterns. Okay, so let us say if you are in the library, of course, the librarian has managed to put, numbers arranged in certain order. You can immediately go Ranganathan classification, whatever classification it is, you can immediately go and look at. On the other hand, let us say for some reason, somebody has sort of randomly thrown all the books, and I say, hey, go and get this book. What will you do? It's a very, very hard task. Okay, so if I have 1000 books, you may have to, on an average, search at least for 500 books to figure out the title. Okay, and what Grover did was he sort of devised an algorithm which will work on quantum computers of the order of the square root of the list size. Okay, just to give you, if I have a list of 10,000 books arranged randomly and an average, of course, in some cases, the first book that you see may be the one that you are looking. It is also possible it's the last book another day you may be looking for. Okay, and an average, it's about 5,000 books you have to calculate. Whereas, you have to search. If you use the quantum algorithm for 10,000 books, with a 99.999% probability, you will locate the book in just 100 steps. Okay, and just you can see the reduction. So if you have 10 power 10, it will still be of the order of 10 power 10 because you are dividing by 2. On a quantum computer, it will become 10 power 5. Now you see the enormous savings in time and energy, because it doesn't have to do so many steps. It also saves time and the energy both. Okay, this is Grover's search algorithm. Maybe this is I don't think I will go beyond this in terms of algorithm. Now let us look at the status of promising architectures. Where do we actually implement these algorithms? On a quantum computer, of course. And what are these quantum computers made of? Even in a classical computer, finally there are gadgets which hold this information 0 and 1, which we call, CMOS, whatever architecture that you want to call them. So you have superconducting qubits. Of course, they work at very low temperatures, sub-Kelvin, less than a Kelvin. Okay, and who are the major companies involved? IBM, Google, SpinQ. Okay, they all make quantum computers which will work at very low temperatures, and they are sort of being used by people. Okay, for instance, IBM has a quantum computer which has 1000 qubits. Okay? And Google has a quantum computer which is 105 qubits. That is the article that I wrote about, which Vijay shared. And there is a SpinQ, which provides even a tabletop quantum computer with the 2 qubits for colleges. Some of the colleges will have their entire physics lab set up at that money, but this will cost you about 40 lakhs, that one small tabletop qubit. Okay, then you can use trapped ions. You remember I talked about ions and atoms being 2 levels of the atoms being used as qubits, and the people have championed that as well. Honeywell, people who were working, I didn't see that. People who are working with computers in 70s, of course, you would know Honeywell. The same Honeywell company, they are making quantum computers now, of course, small one, 20 qubits, but based on trapped ions. There's another company called IonQ, which has quantum computer which runs with 40 qubits. Atom computing, the claim is they have 1,200 qubits. Okay, and photonic qubits, Xanadu, which is a Chinese company, they have 220 qubits that they can produce using photons polarization states. And the topological qubits, it made a lot of news very recently, Marona, ... lot of questions. That's why I put a question mark. And yeah, we had to wait whether that is a reality or not. But the claim was very, very startling. Okay, and if it is made, then probably it is going to overtake all this, because it is inherently protected from external noise. It can protect its state for a long time. Okay, now what do these quantum computers? Don't think they are sitting on the desktop. And this is a quantum computer with about few tens of ion traps. And this is all the paraphernalia to keep those ions in their position. Okay. So it is never going to be like your palm top computer or anything. And you can see the height of this. This is superconducting processor at IBM. And all this to hold this chip, which can be held in a hand. Okay. It is this chip that is getting there. And to keep it at a very low temperature, you need all this. Okay. And this is Google. Once again, all this just to keep this window inside so that it can work at without errors. Okay. So the computing part is actually very small, but to keep it computing, we need all this additional gadgets working. Okay. Now, what are the two major hurdles in realizing quantum computer? One is decoherence. As I told you, the qubits have to be in superposition. Otherwise, the power is just not there. It is like a classical computer. And this is a very fragile effect. Have you ever seen your friend being inside the college and outside the college? Outside is very often possible. But have you any time noted they are both inside and outside? Probably not. Okay, either they are inside or outside. And there's a good reason for that. When the system becomes big enough, then all these quantum effects get washed out. Okay, this is what we call decoherence. And if you really want to make a reasonably big size computer, and it will interact with everything around, and it's very difficult to control this superposition. They will die down quite fast. Okay. In fact, one of the characteristic parameters to define a good computer is how long they can hold this coherence. Okay. Ion trap computers are the best. They can hold the coherence for a second. Okay. Whereas the other computer, 1 second, that's already a big time. Other computers can hold it for a fraction of a second, millisecond, things like that. But within that time, they have to perform all this calculation. But the idea is that we should be able to prolong it for hours and days, if not for years. Okay. Error correction is another, because it is so prone to external disturbances, errors will happen. It is not that the classical computers don't commit errors. They do commit errors, but they are internally corrected. Okay. A 64-bit machine ideally should not require more than 64 bits, 64 transistors, but you have millions of them, basically because you need to correct for all the errors that build them. Okay. So we need more number of bits basically to take into account all these errors. This is called a redundancy factor. I'm just giving you an example. I'm very fond of this when I teach undergrads. I do this. Let us say a circuit generates 1 in place of 0 with certain property. It is supposed to give you 1, but once in a while it will throw 0 in that place. Okay, this is an error. And when that comes out as an output, that's what you will say, computer has given, and there is no need to worry. A hilarious joke. Once I was filling air to in my car, tire, and then I went to that guy and he was filling it with that computer and said, when was it calibrated last time? Because 1 week before I had filled, it was in the right pressure and it was already above. I said, when was this calibrated? Sir, this is computer, no need to calibrate it. So anything that is computer, you put the phrase in front of it, we trust that is beyond doubt. Okay, not true. Computers can make mistakes, and they do make mistakes. Okay, we correct for them internally. Let us say I want to take care of this error. That is, there is possibility of only 1 bit being flipped or changed. What I'm going to do is 0, I'm going to represent it as 0, 0, 0. That means I need 3 bits to represent 1 bit. And 1, I'm going to represent as 1, 1, 1. I know that any sequence is a combination of zeros and ones. Now that sequence will be 3 times bigger. Okay. And how do I know that error has occurred? Let us say I want to look at this binary sequence. 0, 1 is represented as 0, 0, 0, 1, 1. So I'm going to read in packets of 3. If I read all of them 0, I know it is 0. If all of them are 1, I know it is 1. Let us say one of these qubits has flipped because of this process. Then what will happen? 0, 0, 0 will become either 0, 0, 1, 0, 1, 0 or 1, 0, 0. So in a packet of 3, if I any time find other than 3 zeros or 3 ones, I know an error has occurred. And I also know which digit it is. If it is 0 or 1, and I can correct it. Okay. Of course, for students here, why can't I do it with the 2? It's a public lecture, but still I think I can give problems, homework exercise. Why can't I do it? That's represent 0 as 0, 0 and 1 as 1, 1. Why is it not a good choice? Okay. Take it as homework and do. And this is how we correct. Now, what are the research activities worldwide that's happening? And here is it is actually 2 years old, a beautiful compilation by IIT Centre for Quantum Engineering and Industrial Consortium. Think of any big name in IT, all those guys are sitting over there. Think of any top-notch university, Ivy, Cambridge, University, Oxford, any big place in the world, all these guys are here. Everybody is investing in this technology because there is a sense that this technology can actually revolutionize. What will it do? Of course, it will break RSA. That's a different issue, but it can also help you design cancer drugs. Okay. So it can help you design new materials. It can help you solve, because very often weather prediction is an impossibility almost. It can help you solve that. Okay. It can help you to look at environmental crisis, because very often so many variables are involved. It's very difficult to really model and figure out what is the best way, and quantum computers. And that's what people like. Nobody's planning to use quantum computers to produce cash bills in a shop. Okay. It will all be used for these kind of very, very crucial issues. Okay. And of course, you may wonder, where are we? And here is the thing. It's actually from Department of Science and Technology. It's not that we are lagging behind. Of course, we are not at the forefront like other labs. We have not made a quantum computer as yet, but research has just started, and Government of India is investing close to about 8,000 crores to be spent over the next 5 years, enabling our researchers and research institutes to take up these quantum computing challenges. Okay, and hopefully even there are startups I know which are setting up the shops, and it's an opportunity for students here to jump into it, and for seniors here to invest in them. Okay. And challenges, scalability. So we have made 100 qubits, 5 qubits, 10 qubits, but we need millions of qubits. Without that, you cannot have a practical computer, which could be useful. Error rates and qubit coherence time. This is another issue. So we are looking for people in physics, chemistry, computer science, engineering, electronics, all to come together. It's a highly interdisciplinary area. If you look at the group in Google, you will see everybody except maybe English literature working there. And they come at the end because they are the one who actually communicate to people what it can do. So even they are not left. It's such an evolving technology. Okay. Noise is another problem. Theoretically, we are able to produce wonderful algorithms, but we need suitable computers to implement them. So there's a gap between theoretical prediction. Even Majorana that was talked about a month back, topological qubits. There are theoretical prediction, but how we actually realize them is a big question. What are the opportunities? Opportunities to develop more stable and scalable quantum system, hybrid approaches. That is, quantum computers can do part of the work, which is very hard for the classical computer. The rest of the number crunching can be thrown into classical computer. They can do. Okay. So you don't have to really think of a very huge quantum computer. So it's a part of the problem which can be done on quantum. The rest, the routine number crunching, could be done on a classical computer. Of course, we need advancements in chemical research, material science, and so on and so forth. It will also be useful for all these. To do material science research for quantum computers, you can use a smaller size quantum computer to do and produce better materials to produce bigger quantum computers. So it's kind of a positive feedback that works there. And I don't think these are impossible. This is how our computer started 150 years back, and it could add 6-digit numbers. Okay, and now you know where we are, and therefore anything can happen overnight. Maybe there will be a quantum computer around sometime soon. Thank you very much. And this is my email ID in case you have any questions.
But before we get into the question and answer session, this Anna Sentinel Library want to honor the speaker by giving a small moment out. One is now, I want to make you to become the Tamil Nadu member of Tamil Nadu Science Forum. We are going to display the QR code. Just scan the QR code and fill up the form and send the subscription. It is 30 per year. You will get a subscription magazine from Tamil Nadu Science Forum. Please make sure that you are becoming a member of Tamil Nadu Science Forum. And the second one is we have a registration QR code. Many of you have come directly to this. No, we have 10,000 people in our database. We send messages to all our events. Still, we get some 50 or 60 people. I know people with different interests will come to the different topic. So we want to have your communication address and email ID and and your mobile number. Please go, scan the QR code and register. It will be with the Tamil Nadu Science Forum. We are not going to share it with any marketing agency. It's the purpose only for sending our events to you. So we are continuously conducting the lectures, and every month we have the lectures. We have a lot of programs in Tamil Nadu Science Forum. We will communicate to you what we are doing. With that, we'll get into the question answer session. So, do you have any question in the online?
About that quantum computing. Now, is it why it has not come up to the market? Is it because that when you say the whole operation has been done at sub-Kelvin temperature, I know this is very, very difficult. It's not going to be practical. It may be okay in a lab. And the advantage, that's the first question. The advantage of quantum computing, it's going to increase the speed of or what is the advantage? It's going to make things faster. It will handle a lot of data.
Yeah,
What's the advantage?
yeah. The second question first, you are true. It is both fast and it could handle huge amounts of data, because the way it represents data is very different from the way it is represented. Data are usually represented on a classical computer. That's the advantage. The first part, see, this is the technology, proven technology that we have. So it's not that people are not thinking of newer ideas, which Professor TRG was also referring to, Maron of topological qubits, the idea that has been floating around for 20 years, but the experimental realization has taken so long. And even now, people are not very sure that they have realized. Okay, so it will take time, but remember, prediction in technology is always a big issue. I just recall the story. I think in 1960s, IBM chairperson was asked a question. They had just made a prototype of personal computer, and therefore they asked, how many computers will you be making every year? Apparently he remarked, there is market for about 4 personal computers in the world. I feel that probably there are only 4 houses in the world with personal computers now. Almost every house has. So it's very difficult to predict what will happen in technology, because that time that personal computer was very huge. Now I showed you, Apple iPhone is 1,000,000 times better than that. So technology can improve. And now you also look at the transistor density on a 2 centimeter square, from 5,000 transistors to about 5 into 10 power 10 transistors. So technology can change. So on that front, I will not make prediction. These are all only assessments. In the sense,
is the problem, what has been achieved is a miniaturization of chips.
Yeah.
That is one story.
yes.
But what we face,
Yeah.
what we face in this point is temperature,
Yeah.
lowering the temperature, which is a real big task.
That is
Very
true.
difficult.
It's lowering temperature. And as I told you, the quantum effects are usually very fragile, superposition and other things. Even with that, they could actually decay away. The coherence time is a fraction of a second. So how do we actually extend the coherence time? That's a big issue. So Majorana qubits is one where they can stay in that coherence superposition for long, but how to experimentally realize them is another question. So that's why I said there's a gap between theoretical ideas and experimental realization. But I'm sure somebody will address. Youngsters are here. I'm sure some of them will address.
Okay. Thank you.
Please wait. We are recording, other people are, it's online lecture.
You say that it will take about 10 years for it to mature in India.
Not able to predict.
No, I said
No, that is
that's
approximate
an
time
expectation,
frame.
not in India.
Oh,
Yeah, quantum computer somewhere in the world.
oh,
A reasonably sized quantum computer and a reliable quantum computer.
okay. In that case, how much time would it take in India? Then by that time, whether any other technology will come over and take over.
Possible. Any other technology, I told you, it's very difficult to predict what would become a technology. For instance, nitrogen vacancy centers, which are like basically color centers, they were once thought to be possible candidates. NMR, that is long chain polymers, they were thought to be possible candidates. But they realized the limitation, that the scalability. You can make a 10 qubit computer on that, or you can generate 10 qubits, but you cannot make millions of qubits. But these are the technologies where people invest. Remember, initiating a new research is also very expensive in these domains. So they would like to invest more on those fronts where they know for sure that something can be achieved. So that's how it happens. So remember, IBM, Google, all of them are into superconducting qubits. That's because they are reliably produced and they can be operated reliably. The technology is, that's the reason. But it's possible that some university researcher can actually come up with a fantastic idea. Yes, people will jump on it and grab it.
Okay, another question is, you are saying it will be able to predict the materials.
Material properties, yeah.
Is it material properties or materials production?
Properties, material
Oh,
property.
okay.
All the calculation that we are not able to do now, or we are not able to do at the scale at which you would like to do,
Okay,
all those things it will be able to do.
okay. Thank you.
Instead of using two-state like classical computers, why don't you gradually increase 3-state, 4-state, 5-state like that? Is it possible?
It's possible, as I told you,
Practically.
more the number of states, there are other difficulties that come into play. So in 2 states, it's much easier for control. So I should be able to individually address the bits and change the states, right? So that is possible if I have 2 states. See, no system is with the 2 states except possibly spin, which is frozen at a lattice point. Atoms, for example, they have many states. But the so-called gates, which are essentially electrical pulses, are so chosen that they will connect only 2 states. Other states are there, but having more number of states, remember, I want to put them in a superposition of 1 and 2. It may end up in superposition of 2 and 3. So I don't want that.
Thank you.
What is the
Yeah.
what is the physical device which can hold the superposition? I mean,
It is that I told you this, for instance, a spin can hold the superposition. It is the state of the spin or the atom in a superposition of ground state and first
so
excitation.
physically we can see that.
You cannot see. You
I
can
mean,
do an
conductor
experiment and
is-
infer.
This image we can see that, physically.
CMOS, you can see.
What is that? That quantum,
You can see a chip.
quantum phys
You can see a chip. You cannot see the transistor on a CMOS. It is just a 10⁻⁶ atoms.
The original idea which was used was due to this Einstein-Podolsky, whatever paradox
Yeah.
is, they created a combined angular momentum state, spin up and spin down kind of thing, separated them, but angular momentum conservation will tell you what happens here happens there also. So that is what is used, but that is very difficult to keep the coherence. But that's where the low
I think he's
temperature and
asking
other
about
things
memory,
come.
quantum memory, where the bits
Yeah.
are stored.
Mm.
So the current idea is you read off the information on that, actually store it on a classical computer.
Yeah.
Where it can stay for long. Okay. And whenever you want to read off from the classical computer and put the quantum system in that state. That's how it is done. Because our quantum memory is not long lived. We know the coherence time is at best a few seconds. So it's not going to survive.
which is superposition, how it can behave the two things, but store it in the physical way. I was just
That is the state of the system itself. You don't have to store it elsewhere. That is the way the system is. Just imagine this. You can walk along the, let us say, northeast direction. That is equivalent to moving along north and then east, correct? You are moving along northeast direction like this. You can also go this way and then reach there. A superposition is like this. That is not a surprise. Thing is, now if I ask you in which direction you traveled, it will say you either traveled along north or along south.
it's looking like reverse engineering. I mean, the result is like this, so you actually behave like this.
No, it's the other way. I exactly know through Young's double slit experiment that it is in a superposition.
Very difficult to okay. Yeah, we'll move to a couple of questions in the people online. One is Hariharan. Understanding is simultaneous calculation happen on multiple superposition states in parallel without decohering. Should there be a mechanism be there? How the task must be split in states?
Now, decoherence is a problem, as I told you. It's a big issue. If so long as you have the superposition available to you, you'll be able to perform the calculation. If it snaps, superposition snaps, of course, computer won't work. I mean, that calculation won't work.
The second question is from Vishwa Kiran. He said, as in quantum computing, involves in superposition, is it possible that in future, it can impact mathematical calculation, or it can change the way how we calculate things in real life?
Mathematical, I don't know. Anything that can be converted into an algorithm can in principle be executed by a computer. And of course, quantum computers there will perform well. Let me also give you this caveat.
The third question.
One before that, a related question. Very many times when quantum algorithms were created and claimed to be much better than classical algorithm, most cases, people have always come up with the classical algorithms which perform as good as quantum algorithms. Okay, that means they could improve the efficiency of classical algorithm. Except Shor's factoring algorithm and Grover-Seltz algorithm, for many of the other famous algorithms, you can always find out there are classical ways of doing it. Okay, so it's a very interesting question to ask. Is there a way to always produce a quantum algorithm which will outperform the best classical algorithm? That is not something that we have answered. People to produce an algorithm which, based on current understanding, performs better than classical algorithm, but there are also smart classical computer scientists, and they come up with algorithm which perform, at times they have outperformed the classic quantum algorithm. Okay, that also has happened. But there are also algorithms where we know for sure classical computer can never supersede quantum computers. Prime number factorization, Grover, search, and so on.
The next question, one more question.
That
question
is
from
a
the
very formal proof, mathematically demanded.
online question. The last question from online. Hariharan, you, another question. Will there be drastic changes in how we program quantum computers? Will it be much different from how we program present day ones?
So luckily they have produced interfaces. You can write, for instance, a program in Python, and there are interpreters which will actually convert it suitable for the kind of quantum computer the system has. For instance, you can program IBM quantum computer, which is free. They have 5-bit qubit quantum computer, which anybody can program and run your problem. Of course, they have a bigger quantum computer where you have to pay, but the 5-qubit quantum computer is free for anybody. You can just register with your email ID and you can actually program the quantum computer. They will run the problem and give you the result.
Can factorize 45 years.
No, I think 12 or something, because it has.
So maximum.
So thank you for the lecture, sir. How do you say this information is physical when quantum is not so?
Quantum is also physical.
It's dynamic and it's everywhere.
Or, I didn't get your question.
I mean, it cannot be stored. It's dynamic in a way.
No, it cannot be stored using present technology. My present technology, I'm able to retain coherence only about a second, maybe max.
And
but that doesn't.
The position of it, it cannot be predicted unless you open it.
I don't need to predict. That's the way the smartness in these algorithms. They know it collapses into one of the states when they measure. So the algorithm are so designed that where it collapses will be your answer.
So quantum is physical.
Yeah, quantum. See, a classical algorithm, you cannot write. You replace statements and you get a quantum algorithm. No, it's a very different animal. I think so. Already it is. They are doing small level calculations.
They said it's coming out.
Yeah.
Probably happen in the next 10 to 15 years. In quantum computing, how much space required for random?
Okay.
Please.
In one of the slides, you had shown that the state. Can you hear me? Yeah. The state of the qubit can be represented by alpha times state of 0 plus beta times state of 1. Or the slide also said that alpha squared is the probability of state of 0. Why is it squared?
First, very intuitively, it has to be mod square, otherwise it won't be positive because it's a complex number. Therefore, probability has to be somewhere between 0 and 1. Okay, and it was actually an idea put forth by Max Born that these probability amplitude square should be the probability, and there are some theorems in mathematics which are sort of convinces us probably it's a good way to do. Yeah, but it's an interpretation. Interpretation is something that you cannot prove. Vacuum space. You cannot avoid switch off vacuum. That is one of the lessons of quantum mechanics is you can switch off this light, but there is something called electromagnetic vacuum that will disturb the atom. That's why atoms emit. There is nothing like switching off everything. Is that it? Okay.
So,
Yeah. Now, if we can actually switch off, then all problems are solved in one go. What?
so I'm not quite able to understand the transition between quantum computing and quantum entanglement and superposition of states. Sir. How do we apply those superposition in the quantum computer, sir?
I have not written down the algorithm. If I had written down the algorithm as to how exactly the steps are done, you will see the superposition. But the key idea is all the inputs are simultaneously represented. If you remember, I had 0, 0 state plus 1, 1 state, right? So on a classical computer, you have to give 0, 0 as the input, get the output. Give 1, 1 as the input, get the output. You have to do it twice. On a quantum computer, if I can send the state as 0, 0 plus 1, 1, it will calculate the output for both of them simultaneously. So I'm just giving 2, therefore, how does it matter? 2 calculation, 1 calculation. Just imagine 10 power 20 calculation. On a quantum computer, it will be just 1. On a classical computer, it will be 10 power 20 calculation. Provided you have so many bits, of course. It's not that in every calculation we need only 1. There are some places where even in quantum computers we do many calculations, but still it will be much more efficient way of computing compared to a classical computer.
This is the last question. We'll have this as the last question because people would like to go also. After that, you can meet for some more time.
I'll be around.
You can bother.
Yes, sir. Will normalization be the constraint of making a quantum entanglement state?
All the states, though I have not written down, it is all normalized. I just wanted to avoid that because it's a public lecture. I don't put that number in front, but they are all normalized. No, that is not even, no, without normalization. That's what he meant. It has to sum up to 1 mod amplitude square. It's not a constraint. That's the way state is. That is possible.
What is happening is definitely 1.
Yeah.
That's all. The fact that you exist, you will exist somewhere. The probability is 1. That's what is used.
What I'm asking is, since alpha and beta can't be any random values.
So this should sum up to alpha square plus beta square should be equal to 1.
So we can't take alpha beta to be random. If alpha is something, beta has to do.
No. Let me answer it this way. Remember, this is a normalization, overall normalization. Okay, this is a number between a complex number on the unit within the unit circle, such that sum up to 1. Now the unit circle is as big as the whole plane. You can do a mapping, so you are not losing any generality. 0 to 1 is as big as 0 to infinity.
Just the conformal mapping.
No, it is just a mapping. It's not a conformal. I don't need a conformal map.
In the classical computer, we use the diode for transmission that one point. Last in quantum computer,
Here.
Excuse me.
Others should hear your question now.
So in the classical computer, we're using the diode for transmission one way. In that quantum computer, same way we're using photonic diode for superposition.
Basically, that's the diode. My electrons
Diode is basically for a rectifier or things like that. One way where that is current moves, but we don't need such a process in quantum computation.
But how? Because if you're quantum computing using that photonic diode kind of thing, it will be one way.
I'm not saying it is using photonic diode. It uses photons, electromagnetic field. I'm not saying photonic diode.
X-axis or y-axis or a combination also. That's what.
But using some berry phase or something.
No very phase.
It is just a polarization.
So okay.
Arbitrary directions between
Okay.
X and Y.
Okay.
Okay.
So you know using that photonic diode.
No.
Not on a quantum computer.
Okay. Thank you.
Okay.
So
You have a question?
yeah, it's
go
not a
ahead.
question, it's a kind of small remark. So we have been attending so many lectures in different places. Some lectures will be useful, but may not be beautiful. Some lectures will be beautiful, but may not be useful. But your lecture is a superposition of both useful and beautiful. Yes, it's a superposition.
Problem. If I make a measurement, it will be either good.
That is your remark. So my question is, as a teacher, so would it be possible to make a kind of undergraduate curriculum as a quantum computing?
I do teach such a course at Kriya. You can easily teach quantum computing. In fact, I have been, last week or so, I was in Pondicherry University. I was telling them like the best way to introduce quantum mechanics is not the conventional approach. You should introduce qubits, just to 2 levels, teach them what all can happen quantum mechanically. Absolutely, yeah. That is the right way because the mathematical complexity is taken off. Therefore, they gain conceptual maturity. Subsequently, you do hydrogen atom, helium, it will all be cakewalk for them. But on day one, you sort of threaten them with hydrogen atom, they are not going to, because the mathematical difficulty actually hampers their learning of conceptual structure.
You can suggest a few reference or maybe some
Absolutely.
for this.
I will send them.
So that thank you.
Yeah.
Okay, thank you very much. At some stage, we have to close the talk. So, okay. So, no, you will propose the word. So, this will be the end, but he will be available for some more time. Don't bother him. He has to go and have some lunch also. Okay. So, with that, we'll have. But I wanted to make one final profound remark. The laws of quantum mechanics is the only thing. The classical is only approximation. You obey quantum mechanical laws. I obey quantum mechanical laws. Everyone is obeying only, there is only quantum mechanics, quantum theory. Classical theory is an approximation of the quantum theory. Most of them is enough. So this is a thing, probably if you can think about it. Now I request Aditya to propose the vote of thanks.
So we are very grateful to Professor